Okay, students, let's get going. For today, we're going to talk about angular momentum, and that's our main topic for today. And it's in the textbook on a chapter on angular momentum. You can read a lot more about it than what we'll talk about in class. I'm going to give you some examples from astronomy, or I'm going to point you towards some from astronomy. And also I'm going to point you towards some examples from a big lecture hall at UCF. But before we do that, let's just review the SI situation. Now, we have regular SI this week with Yaz. And did you have some students on Monday?
Yeah.
Okay, good. There's also, as you know, there's an exam coming up a week from today. Okay, and it'll cover all the way up to Thursday's lecture, plus any homework that I assign. And hopefully next Monday, Yaz will have an extra or an extension of SI to be an SI review session. All right, and even if you can't go to the regular SI, you can go to the SI review. Definitely go, because even if you go for like half an hour of the SI review, it's going to help. All right, so try to get yourself over there. And we don't know the room yet or the time. It's still pending. But by Thursday lecture, hopefully, we'll have something special, and you could put it in your calendar and attend that. So and Yasmin's done a great job in previous semesters, and she's doing a great job this semester. So I highly recommend that. Now, last time we were talking about this idea that there's two different kinds of momentum. There's the translational, straight ahead from point A to point B, covering a certain distance in meters, kilometers, or light years, or anything like that. P equals mv. And there's also one associated with something that might not be moving. It's just spinning in place. If you think about it, anything that's spinning, it might not be, it's got a lot of motion, right? But it's not going from point A to point B. It's going around and around in a circle. Every little molecule in that object is going around and around and around in a circle of various sizes, depending on how big its radius is and its other dimensions. But we took a look at this, the spinning crescent wrench that is moving translationally. It looks like from left to right, although it's a strobe photograph, you can't really tell usually if it's moving from left to right or right to left. But if it's moving from left to right, then it's also spinning. And we talked about the center of mass, and how the center of mass of the crescent wrench, where those little black plus signs are, is going just straight ahead. So many centimeters per second, or so many centimeters between each strobe flash. We talked about this one, this daredevil motorcyclist. And if you look at that carefully, you can see that he in this one, look at this. I mean, this guy is a maniac. Look at that. His bike is up here, his feet are below him, and his bike is above him. Can you believe the adrenaline rush doing that? I've done some crazy things in my life, but man, I tell you what, that'd be a rush doing that. And then he makes it look easy. He gets down over here, smooth as silk. Well, we don't know for sure because you can't tell what happens off to the left side. Same thing with this guy. He doesn't do the handstand, but It's a combination. Now this is not constant linear momentum. The momentum is changing. The P equals mv momentum is changing because he's going up and then he's going back down again, but he's also spinning. And the idea is that the angular momentum, as well as the linear or translational momentum, are both things that can be conserved under certain conditions. All right. And what I want to show you right now is a little web page in YouTube. Go ahead and switch over to switch back to the playlist, please.
Oh, the playlist?
Yeah. Okay. We're going to look at a demonstration.
Which one do you want?
Go back a page. Go. Yeah. Click out of that. All right. Go to the top. Uh, this is the angular momentum playlist. It's in our YouTube area. And let's go ahead and play the first one. And just to give you a flavor of, go ahead. That's me. This is over in 207, Classroom Building 2, 207. And the maniac at the camera, it hasn't figured out how to focus it yet. There we go. I'm the maniac at the camera, operating the camera. So this guy here is standing on, and we're going to be doing this on Thursday down here in the front. So everybody will have a chance to try this out. It's kind of a cool demonstration. And there's Carol. Right, this is Caroline, my TA from a few semesters ago, from the Mighty Psych department, one of my best TAs. And she's holding this bicycle wheel. You'll see the bicycle wheel in a second. And it's spinning. And it's got two handles on it. Man, this is pretty pathetic. This film, I filmed it, if you haven't figured that out. All right. So there's the bicycle. When he flips it, he starts spinning. He wasn't spinning. He's spinning the same sense as the wheel was spinning. Now he stops. And this time, I want you to take the notes. Does that sound like me or what? Nagging everybody about notes. All right, now it's really going. He flipped the wheel. We're going to analyze this. This is the, and watch this one. What he's about to experience. Flip. Stop. Flip. Back again. Let's go the other way. Flip. You really notice it there. Flip. Slower. Flip again. See how he speeds up? Gosh. I totally have. Okay, we're going to be doing that one and a few other demonstrations. I'll go back to the laptop. On Thursday, we'll get that equipment in here for you. And just so you know, it's down towards the bottom of our YouTube area. So if you click the playlists button, you'll see a bunch of different playlists. And angular momentum is down there. You see different semesters and whatnot. Um, and this is a demonstration that anybody can do. Okay, and so we'll ask for volunteers from the audience and stuff. And it's pretty fun. And there's different variations and stuff like that that we'll do about it. So we're going to be doing that on Thursday, as a demonstration. But what I want to do right now is give you some kind of an idea of what the physical quantity is in terms of regular momentum and angular momentum. So as we said last week, the rotational analog of the F equals ma force is called the torque. Okay, and that's another word for that is leverage. All right. So and that's why when you have a wrench and you're trying to break loose a nut on a machine and it's rusted in there, sometimes you got to go get a bigger wrench, get a little more purchase, a little more leverage on it. The force changes the momentum state, and so therefore the rotational analog to momentum is changed by a torque, and that quantity is called angular momentum, and it is a conserved quantity. Now, if you look at this set of equations, the first one is F net equals the quotient delta P over delta T. Now, that's Newton's second law. That's F equals ma, but written in terms of the momentum. And we're going to do a similar thing with torque. It's going to be torque equal to the quotient of angular momentum over delta T. And there are two kinds of angular momentum that we're going to try to get a kind of a concept of. The first one is called orbital angular momentum. And that's the momentum that has a sense of spin relative to a central point or even a central axis. So planets orbiting the sun, they have an orbital velocity. They're going so many miles per hour, so many kilometers per second. They're going pretty fast. All right, so that's P equals mv, but they also have the sense that they're rotating around the SUN, and the SUN is that central point. And the spin axis, you may not realize this, but all the planets in the solar system, they're all in just about the same plane. And they have different size orbits. Mercury's in close, and Jupiter's way out there. Uranus and Pluto is no longer a planet, but they're way out there. And comets, they have orbits around the sun, elliptical orbits. The asteroid belt, all those little asteroids in the asteroid, and they're all about in the same plane. And so their axis, and they're all orbiting the SUN. So the axis that they spin around is the one straight up from the SUN. So think of the sun at the center, and then choose some star up there, way out there above the SUN, and that would be like the spin axis for our solar system. Okay. Our Andrew asks, is our galaxy orbiting? Yes, we're in the spiral galaxy known as the Milky Way.
Is it on a similar plane?
It's not as good a plane as the solar system, but it is disc shaped. It's got a little bit more thickness to it, and there's other things rumbling around and stuff. But yes, it's a spiral that is formed into a disc shape.
Are there comets that, I know this is a little into the weeds, but do we have comets that enter our solar system
from above?
From the y-axis.
The question is, do we have comets that enter the inner solar system from other angles than just on this plane? And the answer to that is yes. We have there's a pool of comets way far out in the solar system. It's called the Oort cloud, Oort, And if you want to study more about that, take Astronomy 2002 next semester, which you might get a section with me if you take the online section. But the Oort cloud, yeah, you could have comets coming in from all, but Halley's Comet, the famous Halley's Comet that we talked about last week or 2 weeks ago, I guess maybe, that is in the same plane. That's roughly in the same plane, and that's related to comets. There's another zone of comets outside, way far out from the planets, called the Kuiper Belt, Kuiper, named after Professor von Kuiper from the Netherlands, who kind of figured out where it had to be. And we've since verified. What was that? Whoa. Uh, so yeah, and all that is from conservation of angular momentum. And so even if you're dipping in from an angle like a comet from the Oort cloud, you're going to keep on that orbit until something bumps you out of the way, or something like that, or till you blow up. And our planets have been in the same plane, for zillions of years, pretty much.
So could they have started out on different planes, but the gravity of
And
the
that,
sun just pulled them into
so the question is, could they have started out in the same plane? Yeah, they could have. And we think that everything in the solar system did start out in a disc-shaped blob of material, and that some of the stuff, gets perturbed and way out into these outer weird orbits, but most of it stayed in the plane. Now, let's keep going. The second kind of angular momentum is called spin angular momentum, and an object is, and that this wheel, this disc up here is a good example of that. It's spinning about an axis through its own extended body. And this, in the textbook, I mentioned the fact that Aristotle always believed in his day that the motion of an object that's flying through the air was like an arrow, was caused by air rushing behind it and pushing it forward. And then more air coming, and then the arrow moves a little bit, and then more air comes back behind it and pushes it forward, which is appealing. It's nice, but it doesn't make sense for something like this, because there's no way for any air to get behind this. This is the object that is behind itself. All right. So this is something that, had Aristotle thought about this kind of a disk, which he could have, I'm sure, they had wheels and stuff. He would have thought differently about this idea of air coming around from behind the arrow and all that jazz. So let's take a look at close up at orbital angular momentum, and we're going to do some diagrams here. So be ready to make some sketches in your notes. So the fixed point of interest in our solar system is the SUN. All right. So go ahead and draw a perspective view like this of the sun, and then there's Earth, and give Earth a nice circular orbit, and it looks like an ellipse because it's perspective view. And did you know that the strongest color, all the colors of the rainbow that come from the sun, red, orange, yellow, green, blue, indigo, and violet, the brightest one is kind of yellowish green. And so that's why, so our sun is actually kind of a greenish star. And so that's why I always make it look green in computer slides in this. Now, when we're looking at it from inside our atmosphere, it doesn't quite, it looks white. And there's reasons for that. But, you could have a comet. So here's a comet on an elliptical orbit. Now, we're not going to go too much into detail about the comet and the ellipse, but for an elliptical orbit, an oblong ellipse, the sun is not at the center. It's at what we call the focus, one of the two focuses of the ellipse. So there's the center of the ellipse, which would be right about, let me turn around a little bit. The center of the ellipse would be right about here, maybe. Yeah, right about here. But the sun is down here at one of the focuses. And there's another focus over here, symmetric, and you can graph it out on graph paper. We may do that at some future point. And there's nothing, this is just a geometric point, but this is a physical location for the SUN. And so if you're on an elliptical orbit, you have angular momentum. And you also have linear momentum. I mean, you're moving on a path. You're moving on a curved path. So your speedometer reads so many miles per hour, so many kilometers per second, right? And so what you have to take into account for orbital angular momentum is the distance and the angle from that point, the sun, out to the planet or comet or spacecraft or whatever it is you're studying, all right? And you also have to take into account the velocity. Now, I told you that this was the rotational analog to regular momentum. And it partners up with the force. But the rotational analog of force is torque, and that's leverage. Okay, and so as we mentioned last week, leverage depends on where and in what direction you yank on the wrench or that you push on the door. All right, and that distance from the pivot point, the more distance you have, the more leverage you have, the easier it is to turn. All right, and so that distance is up here, and let me turn around here. In this term here, the distance, that distance is the same as the distance that you would consider for a wrench. You know, from the center of the nut that you're trying to wrench out to where you grip it. So whether that's 18 inches or 6 inches or any other distance, that's required to calculate a torque. Now we're not going to do all the trig and stuff for torques, but we are going to talk about the concepts of it. All right. So now let's put in the velocity for Earth. All right. So there it is. Go ahead and put a velocity vector, red one, for Earth. And it's pretty much perpendicular to that radius. All right. Because the Earth's orbit is pretty circular. It's a very, very small amount of ellipticity or eccentricity, but it's so hard to differentiate from a perfect circle that I normally just draw it as a circle, but theoretically you can measure it, the eccentricity. All right, so it's perpendicular out there. Now on a circular orbit, the velocity, just like uniform circular motion, it's always perpendicular to whatever the radius is, the radius to that position. Right now, if you have all those factors, then you can calculate the orbital angular momentum, capital L. There's a symbol that we typically use. Sometimes you see other symbols, but we're going to use capital L. And the angular momentum is an mv with the distance r squeezed in there. All right? Regular momentum is mv. And force is the quantity that changes the momentum state. For us, angular momentum is an mv with an r in there. And that's the thing that if there was some leverage on that object, you could change the orbital angular momentum state. And a student up here in the front was asking, well, are there other orbits that are possible other than the ones in the disk of the solar system? And the answer to that is yes. If it collides with something, that'll put a few seconds of torque on the planet that it collides with, or the comet, and just completely change its orbit. It might go from a nice circular orbit to a really elliptical one at a different angle, some steep angle. So now the position vector R and the velocity vector V on the Earth's orbit are perpendicular. All right, so make a note of that. Now, if you're out there studying the comet, it's a little bit trickier. All right. Now let's take a look at, before we go to the comet, let's pause for questions here about the Earth's orbit. Yes.
I was just wondering if you could further explain what you mean by position vector R and velocity vector V. I'm guessing that just means
from the center of the sun out to the center of the Earth. That vector, that's position vector R with the arrow.
Radius, right, of the
It's the radius. You could call it the radius vector or the position vector along the radius.
Okay, there's labels then.
Yeah.
My bad. I thought they were there was a concept different.
No, it's just the name of that position vector. There's an arrow from the origin or from the center of the sun out to the center of the Earth. Because remember, gravitation is center of mass to center of mass for the distance.
Okay.
All right, and they're always perpendicular. If it's a circular orbit, now another question on this.
So if it's not a circular orbit, if it's an elliptical orbit, then
If it's an elliptical orbit, it's definitely trickier. Let's take a look at an elliptical orbit. Okay, so here's the overhead view, and so this is like looking down from the North Star. And our solar system, if you're looking down from the North Star at our solar system, everything goes counterclockwise. Go ahead and make a note of that. The solar system, all the planets, the asteroid belt, and a whole lot of the comets orbit counterclockwise when you view from the North Star, from that vantage point. Okay? So here's our comet up here. All right? And the trouble with this is that you have to do a little bit of trig with this. And we're going to do a little bit. We're going to do some right triangles here, I guess. But the sun over here is at the focus. Now remember, as I mentioned, there's another focus out here. Geometry. If we were in geometry class, we would put that other focus out there. But we're in a physics class, and so the physical meaning of this focus out here is zip zap. But the physical meaning here is that's the location of the SUN. All right. So the comet and the Earth, they orbit the sun, but the sun's not necessarily at the center of every orbit. It is at the focus, at one of the focuses of each orbit. All right. Now, this point out here, where the comet comes closest to the SUN, is called perihelion. Perihelion. And what that means is, peri means kind of above or next to in Greek. And helion mean that's for the sun, helios, the sun. So that's the point that we would call closest to the SUN. And you know, gravity's pretty strong down there because they have a pretty small R. So the comet is really whipping down there. But now the other symmetric point to that is out here, the far end, way out there to the left. All right, and that's called aphelion. Aphelion. And that's from the Greek root word apo, meaning away, and then helion, helios, the sun. And so another Greek word for that uses apo is apostle. That's somebody that's sent out. And aphelion is the point way out away from the sun, sent away from the sun. All right, now here's where the trig and the complications come in. Draw a line from the comet to the SUN. And I'm going to call that the position vector R. Now, this is not a radius, but it is a position. All right? And so there's your position. And that's kind of our leverage distance, our notional distance for computing leverage to change angular momentum states and so forth. And now, tangent to the comet at the point of the comet, trace in a red velocity vector. All right? And this comet's going clockwise, so this is kind of a contrary comet, and we got comets that go counterclockwise, that go clockwise in the solar system. So there's a comet. It's heading for perihelion. All right. Now the gravitational force is going to be toward the sun. All right. And so it's going to be directed along this line back towards the sun, and you can see that the force has got some newtons parallel to the velocity. It's got some newtons perpendicular to the velocity. It's kind of slanted, all right? It's toward the sun. It's not parallel to the velocity, but it's going to add speed to the velocity, and that's what happens. On this orbit, you get faster and faster until you get down here to perihelion, and that's your maximum speed. And then you start slowing down, and by the time you're way out here at the aphelion, you're really slowed down. But then once you pass aphelion and you start coming around on the top end up here, yeah, you're going to start getting more and more speed, and eventually you're going to be really cooking. And then you're going to be back down here to perihelion. Okay? Now, to figure out all this stuff and figure out the angular momentum at this point, some generic point, not aphelion, not perihelion, but just somewhere up there in the first quadrant, it requires a trig out the wazoo and a bunch of calculus. All right, so now we're not going to be doing anything with that. But you can at least look at the picture and realize, yeah, we can, students in physics 2053 could handle it, 2048. But we're not allowed to do any trig or not much trig and no calculus in this class. So, but on, so here's my last comment on this. Circular orbits are a walk in the park because L is equal to MRV everywhere, all right, on a circular orbit. But that's not always true for an elliptical orbit. So, but to get the orbital angular momentum, L equals whatever it is, you got to do a bunch of trig. But circular orbits are pretty cinchy. All right. Now, questions for this elliptical blurb? Yes.
So in a situation like this, where we'd be given the mass of a specific object, like if we were trying to find,
no, I'm not going to make you calculate anything on this.
Okay.
I want you to look at it, think about it, and maybe make decisions about, well, is it speeding up? Is it slowing down?
Okay.
That kind of thing. Okay. But to do the calculations, no, that requires a little bit more than what we want to do. I mean, if we had a full year, I could get you guys ready to work at NASA, down at Mission Control. And but did you guys hear the news? Katherine Johnson from Hidden Figures, she died just a couple days ago. We talked about her. She was 101 years old. Boy, what a wonderful person, and she's an inspiration to me because a lot of the same stuff I research is what she was specialized in. But she was the boss. Nothing else to say about it. All right, let's talk about spin angular momentum. Okay. That was orbital. So you can think about orbital angular momentum as something like what a planet has going around in a circle or maybe an ellipse. Circles are easy. Ellipses are kind of tricky but doable. But now spin angular momentum is a little bit better. And here's the technique that we're gonna use. We're gonna break up a solid object mentally into a bunch of little pixels. And so what we're going to do is for every pixel in this disk, every gram of mass. So break up the thing into a zillion little grams of mass, however many there are in the object, and then it's going around in a circle, around an axis. So that's L equals MRV for that one. So that was easy. All right. And then you just do that for a bunch of little pixels and add them up. All right, now here's the thing about it. If it's a rigid object, now the solar system's not rigid. It's more like a fluid, different speeds, different places. But if you do have a rigid object like this disk, everything has the same angular momentum. It has the same number of RPMs. So it might be spinning at 600 RPMs. All right, but depending on how close you are to the spin axis, you might have a lot of speed, of orbital speed. Your V might be big if you're um, far out, and it might be small if you're in close. Because if you're in close to the axle, you're going a little circle with a very small radius in the same amount of time, 600 times a minute. So you're not really moving very fast there. But if you're way out on the edge of the disk, then you're at maximum speed for that disk. You got a lot of you go one circumference way out there at the edge of the disk. You're really cooking because you're covering it the same amount of time. Whatever the period is, and we're going to calculate that in a minute. Now, something else I want to mention to you: electrons in atoms have intrinsic angular momentum. And in other words, the physics, the orbital interaction and spin interaction, like you saw in the YouTube, we observed that with electrons, and it has various, like the radiation emitted by the electron is changed slightly, so we can measure that. So we know that electrons have intrinsic spin, but we don't understand why they have it. We don't understand it. The Russians don't understand it. Nobody understands it. But we know it's there. But that's the way the universe is made. It's little orbital chunks of orbital of spin angular momentum. The momentum of spinning. Here's something else that's kind of cool. Photons of light. The little particles of light that are entering your retina right now. They have spin as well, angular momentum. And there's different ways to explain the fact that they have it, but we don't really know why they have it. But they do have it, angular momentum. So let's take a look at the rotational motion. And here's where we're going to break things down into pixel. All right, into pixels, little tiny. So every point on a rotating body has the same angular velocity omega. So 600 RPM or 5 RPM or whatever it happens to be. Okay, and the symbol for that is this kind of curvaceous W. That's a lowercase omega. And omega is simply, for instance, the degrees per second. So the change in the angle theta per second. All right, so if you have a lot of delta theta per second, then you have a lot of RPMs. You have a lot of angular velocity. All right. So now here's the point I was making before. Two different points at different distances from the axis of rotation, even though they have the same omega, they'll have different V. All right. They'll make one revolution, but something out here, like point number 2, it's going to make in one revolution, it's going to cover a lot of centimeters. All right. Versus down here, point number 1, it's a little bit closer in. So one revolution for it is a little bit smaller, okay? And they both cover the same one revolution in a certain amount of time. So that gives you the orbital speed. And that's how we're going to take this thing apart. All right. Um, so let's take and um, we're gonna actually use a wheel to figure this out. Okay. The special kind of momentum that you see when an ice skater at the Olympics spins, and you've all seen that. Matter of fact, saw spin angular momentum in that YouTube video. All right. Think of a bicycle wheel spinning on its axle. That was in the video. All right. Now, here we go. We're breaking it apart. All right. I want you to follow closely. So we're looking at this wheel. Every centimeter of the tire is like a pixel, and it has a certain number of grams of mass, and it's going to have some speed, depending on how fast the wheel's spinning. All right. And therefore, it's going to have some MV. But it also has um, an orientation to the axle. Okay. So you might have a 26-inch rim, so you're about 26 inches away from the axle on your bike tire. All right. And so even if the wheel's not moving from point A to point B, like when you're riding a bike, if you're just spinning the wheel, you still have P equals MV, and you're going to have pixel by pixel, you're going to have some MRV. Now think about that. We're just looking at the tire. We're forgetting about the spokes. You can do the spokes if you want, but let's just think about the tire because that's where most of the mass is. All right. Every centimeter has got a distance r from the axle. It's got some grams of mass, and it's got some v. So that means it's got some MRV. All right. And that is the conserved quantity that we're going to put together. We're going to analyze that into pixels and then put it back together. All right, so here's another picture of an ice skater. The conserved quantity is angular momentum. And so the ice skater is going to keep spinning, and he's on ice. He's got steel blades. Is anybody here an ice skater? Ever trained as an ice skater? I mean, it is Florida, but I imagine they have really special steel for or even titanium for their blades, for a professional ice skater. But on ice, it's going to be really slick, so there's not a whole lot of friction. And the same thing with planets. Now, here's a topic, exoplanets. Those are planets that we've discovered orbiting nearby stars. And we found a whole bunch of them. Here's one of them, the TRAPPIST-1 system that they discovered a few years ago. So this is the artist's conception. It's not to scale or anything. You can read about it in the 22 February issue of Science of Nature, the journal Nature from 2017. Go ahead and write a note about that if you care to look at that. This picture is from that, and that's what we do. We look at the light from a star, and when we see the light from the star, we're looking at it for long durations. If we see the light dip a little bit in intensity, that means there's a planet going in front of the star. It's blotting out just a little bit of the star. And that gives us we look at that, and then a few seconds later or a few days later, the brightness goes back up to normal. And then it repeats. It dips and then brightens, and then it repeats again. It dips and it brightens in a certain period, and that it allows us to figure out the orbital period and so forth of a star. So over here, or excuse me, of a planet orbiting star. So right here, these are what we call the light curves. We look at a star for a long duration, and we try to count the dips in the intensity. And TRAPPIST-1 has it's got 7 regular dips. You know, if you look at it for a week and a half or a year and a half, you're going to see the same 7 dips at certain frequencies, at certain time periods. All right, and that's how we tell what it is. For these diagrams, you can look at this article in Nature, and this one's a technical one, so you can look at the pictures. Don't try to look at the calculus in it, though. But definitely look at the pictures, because they do tell you a little bit, tell you quite a bit. Here's a close-up. Here's what we think those planets are doing. So the central job here, there's the star, okay? And then this is kind of what we think the orbits are for all these planets going around. Now, this one out here, we have in 2017, they'd only seen a part of its orbit, but these other ones are close enough that they've seen quite a bit of each of their orbits. Right, so they have a fairly good confidence about that. But that's what we're talking about. Now, let's get down to the nitty-gritty. All right, angular measurements. All right, now, everybody knows this. For one full revolution around a circle, clockwise or counterclockwise, that's 360 degrees. All right, and so revolutions, are 360 degrees. Now, I'm going to introduce a new method for measuring that angle, and it's not going to be in degrees. It's going to be in what we call radians. This is kind of like the difference between Kelvin, or between Celsius temperature scale and Fahrenheit. Okay, so Fahrenheit, 32 degrees to 212 degrees, 100 degrees, 180 degrees of separation between freezing water and boiling water. Celsius scale, 0 Celsius and 100 Celsius, 100 degrees of separation between freezing water and boiling water. And in the radian system is designed by this, or in this way. It's equal to the ratio of the circumference of the circle to the radius, all right? Or to the arc length, if you only have a fraction of a circle, the arc length of your fraction of a circle divided by the radius. Okay, so one full revolution is 2 pi. So in the degree system, 1 revolution is equal to 360. In the radian system, 1 full revolution is 2 pi radians. So pi is equal to 3.14159, blah, 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 blah. So 2 pi is about 6.28. So we would say 1 revolution in the radian system is 2 pi, or about 6.28. All right. And if you have, so like 90 degrees would be half of that, no, a quarter of that. All right. So 2 pi divided by 4, that would be pi over, let's see, 2 pi divided by 4. What fraction would that be? Pi over what? 2 pi divided by 4 is the same as pi over what? 1 pi over what? Think. Huh? Pi over 2, correct. All right. So and that was my next question here, half circle. Half circle. Clicker time. Get your clickers out. All right. So 2 pi is the same as 360 degrees. All right. Pi over 2 is the same as 90 degrees. So question number 1 for today, Just kind of give you a mental workout here. How much is half a circle? 180 degrees. So go ahead and type in an answer. Pi, pi over 2, 3 pi over 2, pi over 3. You had such a look on your face. Yeah, you don't have your iClicker today? You're gonna have to. We only have a few questions today, so hopefully you'll be all right. Remember, you only have to have 85% participation. So you're here most every day, though, right? And you usually have your clicker, right? So you're probably okay. All right, 10 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, let's see what you guys have got. Oh my goodness. It looks like you guys are geniuses. Very good. All right, so half a circle, 180 degrees, pi radians. All right. So that's this. All right. So that's a fraction of a circle, and you can do that with any fraction that you want. Now let's work out how we do it. If you didn't get that one right, um, here's how we do it. So the angle in radians is equal to the arc length divided by the radius. Okay, if you're only going halfway around the circle, it's not 2 pi r, it's just pi r. And then divide by the radius, that's equal to pi. All right, so here's half a revolution, not 2 pi r, but just pi r. And then here's, oops, let's do this again. All right, so there's your, so then you just cancel the r's top and bottom. And you can kind of mentally do the arithmetic once you get used to it. Now, this is something that you see a lot in trig class and calculus class, and there's various reasons for it. And we're going to use it, but not a whole lot. But I do want you to know kind of how it works. And you can always use this proportion. Pi over 180 is equal to the angle in radians divided by the angle in degrees. So you can go from degrees to radians if you want, using this proportion. Make sure you jot this down. This is basically it. All right, now I'm going to ask you another. Now I'm going to try to burn your brains. It's going to be a brain burner, okay? But I just want to see if you guys are still geniuses or not. So let's see. All right. Question number 2. In radians, one full 360-degree revolution is 2 pi. How many radians is this 20-degree angle? All right. All right. Another fraction of a circle. A fraction of a revolution. All right. So do it on. Talk to your neighbors. Consult with your neighbors. Kibitz with your neighbor. Give them some mental counseling. If you're not sitting next to anybody, then you have your own counsel. Now, this is a math topic, and so it's not really physics, but we use it a lot in physics, and I want you to have a little bit of facility with this. All right? Oh my goodness, it's already 2:30. I've been having, I was so tired when I got in here. I thought, oh man, I wish I could take the day off. But I said, no, I'm going to come in here and be a good and faithful school teacher. And it's gone pretty fast. Good. I see a lot of you guys checking your. Hey, who has a calculator where you could do algebra on it? Anybody? You know, cancellation and stuff. Nobody. All right. As soon as I get out of here, I'm going to go get a smoothie. Another 15 minutes. Okay, 30 seconds starting now. 20 seconds. It's good. I see everybody pointing at the diagram and getting at the calculator and stuff. That's what I want. 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Are you guys in? Are you guys in? You good? All right. All right, let's see what you guys. Oh my goodness. You guys are unstoppable. Very good. Yeah, the correct answer here is C, and you guys did a good job with that. And just so you know, here's the proportion. If you didn't get it right, or even if you did get it right, go ahead and jot down this proportion. Because sometimes, you know, you might want to do one that's a little trickier, that's not nice round off numbers and stuff. But yeah, pi over 180, and then your angle in radians and the given angle in degrees, which was 20. All right, so then cross multiply, as they say, and then I flip-flopped it left to right as well. So you get 20 degrees times pi over 180 degrees, and then just reduce. And just leave pi by itself. I mean, treat pi like a symbol that. But if you want, you know, you can, you know, pi divided by 9 is about 0.349. So that's certainly righteous if you want to do that. Okay, so there's your solution. And most of you got that. In fact, let me just look at that again. Yeah, 93%. Good. All right. And so there's your reduced fraction. Now, let's talk about RPMs and stuff. Now, a RPM is one revolution, 2 pi radians in 60 seconds. All right? So so that would be the angular velocity, omega. That's a Greek letter omega, lowercase omega. It'd be 2 pi radians, one revolution in 60 seconds. And hey, you guys, we don't normally use RPMs in most of our calculations. We do use radians per second or just per second. Uh, and that's why we're converting this to 60 seconds. But you know, everyday applications, you do talk about RPMs. So, but we can go back and forth in just this way if we want. So in general, the angular. So here's one revolution and here's 1 minute. So that's 1 RPM. And in general, the way to get the angular velocity is to basically know how long it takes to make one revolution, right? One spin on your axis, right? And that's called a period. So that means, you know, watch your disk and count, you know, do your stopwatch for 20 spins. Hopefully it's going slowly enough that you can do that. And then take that amount of time on your stopwatch, divide by 20, and that's your period. All right. Now, this formula here, omega equals 2 pi divided by t, the period, you can cross multiply that and get the period equals 2 pi over omega. So that's just a little cross multiplication. All right? All right, now we're going to get back to that bicycle wheel. Now we got everything in place for doing the bicycle wheel. So let's keep going. So let's say that we have a bicycle wheel that's going at 5 RPM. That's kind of pokey, actually. 5 times a minute. I don't even think that's walking speed, but let's just say, for the sake of a nice round number, 5 RPM. Okay. Now that means, and let's say that it's going clockwise. So draw in a pixel, this yellow pixel up here. Okay, pixel off one unit of the wheel and put a velocity vector tangent to the circle, tangent to its path. Okay, and it's going clockwise. All right. And now we have to figure out the direction of the angular velocity arrow. Okay, now the angular velocity arrow is a little bit different. You can use, for a velocity, regular velocity, you can just use like X and Y graph paper and, plot out X and Y for your series of points and then figure out the distances and the directions and all that. And that works good for V, but for omega, it's a little bit different. We have to use something called the right-hand rule, all right, for this vector, all right? Now look at my hand up here, all right? Remember on the video I was talking about my hand? Now, take your right hand and curve the fingers in the same sense as this wheel is spinning, so clockwise. So this is clockwise curvature of my fingertips. All right? No, don't use your left hand. I saw a guy up here in the second row. He's going like this. Hey, I've done the same thing. So, just because you're writing with your right hand and but you got to use your right hand. And so the thumb is let's do it. If it's this one's going clockwise. So if clockwise, the right hand thumb is going into the computer screen. All right, see where my hand is? My right hand. All right, and you can do the same thing with your right hand. Okay, and if you curve it in a clockwise manner like that, your thumb will go in. That's the only direction it'll go. Now, if we were going counterclockwise, I'd have to turn around like this. See where my hand is? Counterclockwise, my fingers would have to curve like that. And then my thumb points out of the screen. Now, we've got two different possibilities here. If you're pointing out of the screen, counterclockwise, the symbol for that is a circle with a dot in the middle of it. If you're going into the screen, the symbol for that is a circle with an X in the middle of it. All right? And those two symbols are marked down right there. Now, what we've got is clockwise. Okay? So I'm going to put my angular momentum vector right at the center of the wheel. That's where you draw it. Now, we're not doing this in 3 dimensions, but we could. We could sketch it in perspective and stuff. But here's what I'm going to do. See, there it is. I'm burning it in. All right? A circle with an X. That means that my angular momentum vector is going into the screen. All right, so I would draw in a little arrow in that direction. Or I would put a symbol like that to symbolize that it's going in that direction. All right, now, the rotational period is 2 pi over omega. All right, the regular velocity is v, and in fact, v is equal to 2 pi r over the period, capital T. All right. So now down in the denominator, instead of capital T, just slot in there the fact that T is equal to 2 pi over omega. So here we go. Here's my next. So here's my normal speed calculation. 2 pi r, that's the circumference that it spins. And capital T is the period of time it takes for one spin. Now capital T is also 2 pi omega, so you can write it this way. All right. Now look at what we got there. All right. We got 2 pi r on top. That's the circumference. And down the bottom, 2 pi over omega. That's the period. All right. Now, notice anything about that last expression? It's kind of complicated looking, but what do you see? Anything helpful? What do you see? 2 pi's. They're out of here. All right. So go ahead and burn those babies out of there. All right. And so you got r on the top. And you have basically in the bottom, you have a 1 over omega. So remember, division by a fraction is the same as multiplication by the reciprocal. So division by 1 over omega is the same as multiplication by omega over 1. So this means that V is equal to omega R. And now, my wonderful students, we're about ready to put this expression into our orbital angular velocity, or our orbital angular momentum formula. Remember, that was MVR. But we want some spin. We want a spin concept in there like omega. So that's what we're going to put in now. All right? So V equals omega R. And if you think about it, the total spin angular momentum is equal to MVR of every pixel of this tire. We've just done one of them. We've kind of analyzed it down to just one pixel. Now we're going to apply it to all the other pixels. All right? So here we go. All right? L equals MVR. All right? For that pixel. And we know that V is equal to omega R. So if you look at that now, we now have angular momentum with a spin parameter omega instead of a orbital parameter v, the orbital speed v. All right? So m omega r times another. Actually, you can write it this way. M omega times r squared, or mr squared times omega. That quantity in parentheses there, mr squared, pixel by pixel, that is known as the moment of inertia for that pixel about this axis. You know, our angular velocity is going in. All right? And omega is the angular velocity. Now, we don't have the vectorness on here yet, but we can do that. We know it's going into the page. All right? So the way that you think about this spinning object, break it down into pixels, figure out mr squared for the pixel, you know, because it's going to be a certain distance out to the pixel. It's going to have a certain number of grams or kilograms. And then multiply by your spin state, omega. And that will give you the angular momentum. And that will be the same. And we started from orbital angular momentum, MVR. That's for planets and stuff. You can apply it to spinning objects as well. Now, the thing about it is, a bicycle has a ton of pixels like this. All right? So really what you got to do is the moment of inertia is really The sum, and this big capital sigma here, that's kind of a fancy Greek symbol for count up all the pixels. Count up mr squared for every pixel that you got. All right, now on a wheel, you pixelate it out into, every gram of mass, and the distance r and the square of the distance r squared is the same. So this is pretty easy for, for a wheel or a hoop. All right, it's not too hard to calculate. All right, and if you do that for your entire object, figure out mr squared for each pixel and then add them all up, then you can call that the term for that is the moment of inertia, capital I. And now we have a spin angular momentum that's encoded by two different quantities. Now listen, I, the moment of inertia, and omega, the angular velocity. Right? Now we don't have MVR here. We don't have a lot of trig. We've already kind of distilled all the trig in here. It's all in the I and the omega. But this is important. For spin angular momentum, in this way, the object itself has this property I, the moment of inertia. A cube will have a different moment of inertia than a hoop. But all hoops will have a similar type moment of inertia. A sphere, spinning a sphere. You got pixels at all different radii for a solid sphere. So that sum of mr squareds will work out a little differently. All right? But I, make a note of this, I is a property of the object. If you will, it is the rotational analog of mass. Omega is the spin parameter, the angular velocity. There's nothing orbital about it. All right? Now, when we get back on Thursday, we're going to do some dumbbells like this. We're going to do the angular momentum and the moment of inertia for some dumbbells and make some angular momentum calculations. Okay, I'll give you a little bit of homework tonight. You're dismissed. Can you bring the power up to 100%, please? 100%.